There is a kind of light that has been traveling for 8 minutes. It left the surface of the sun before you started listening to this. It crossed 93 million miles of empty space. It passed through the thin shell of atmosphere that wraps around the Earth. And now, some of it is probably touching you. You might be lying in darkness right now, maybe a small glow from a screen, maybe nothing at all. But even in what feels like total dark, there is light you cannot see. Infrared waves from your own body, radio signals passing through the walls, the faint cosmic background of the universe itself, still humming from an explosion that happened billions of years ago. Light is everywhere, it is always moving, and it carries with it something we rarely think about, information from the past. When you look at the moon, you see it as it was about 1 second ago. When you look at the sun, though you should never look directly at the sun, you see it as it was 8 minutes ago. And when you look at the stars, some of them are showing you light that left before humans existed. This is not a metaphor, this is just how light works. Tonight we are going to spend some time with light, not in a hurried way, not in a way that asks anything of you. You do not need to remember any of this. You do not need to take notes or stay focused. If you fall asleep in the next 5 minutes, that is fine. If you drift in and out for the next 2 hours, that is also fine. This is just a chance to think quietly about something that is always around us, something so familiar we forget how strange it is. Light fills our days and shapes our world, and yet most of us have never really stopped to consider what it actually is. So let's just sit with it for a while. The simplest question you can ask about light is also one of the hardest to answer. What is it? If you had asked this question 400 years ago, you would have gotten a confident reply. Light, people would have said, is made of tiny particles, little pieces of something flying through the air in straight lines. Isaac Newton believed this. It seemed obvious. Light travels in beams, it casts sharp shadows, it bounces off mirrors. All of this suggested something solid, something that could be broken into pieces. But then other scientists started noticing things that didn't fit. When light passes through a small opening, it doesn't just go straight through. It spreads out. It bends around the edges. This is not how particles behave. This is how waves behave. Think of water. If you drop a stone into a still pond, ripples spread outward in circles. Those ripples are waves. They can bend around obstacles. They can pass through narrow gaps and spread out on the other side. And when two sets of ripples meet, they can combine in interesting ways, sometimes adding together to make bigger waves, sometimes canceling each other out. Light does all of these things. So the scientists changed their minds. Light, they decided, must be a wave, not a particle at all. A wave of what exactly they were not sure, but a wave nonetheless. And that seemed to settle it for a while. Then came the 20th century, and everything got complicated again. A physicist named Max Planck was trying to understand something about hot objects. When you heat a piece of metal until it glows, it gives off light. First it glows red, then orange, then yellow, then white. The hotter it gets, the more the color shifts. Scientists had equations to describe this, but the equations didn't quite work. They predicted things that didn't happen. Planck found a way to fix the equations, but his solution was strange. He had to assume that light came in tiny packets, not continuous waves, but discrete chunks of energy. He called these chunks quanta. He didn't like this idea. It seemed like a mathematical trick, not a real thing, but it worked. Then Albert Einstein took the idea further. He was trying to explain something called the photoelectric effect. When you shine light on certain metals, they release electrons, but the way they release electrons is odd. It doesn't depend on how bright the light is. It depends on the color. If you shine dim blue light on the metal, electrons come off. If you shine very bright red light on the same metal, nothing happens. No matter how intense the red light gets, the electrons stay put. This made no sense if light was just a wave. A brighter light should have more energy. It should knock more electrons loose, but that wasn't happening. Einstein proposed that light was made of particles after all. Each particle, which he called a photon, carried a specific amount of energy. Blue photons had more energy than red photons. That was why blue light could knock electrons free and red light couldn't. It wasn't about how many photons hit the metal. It was about how much energy each one carried. So light was a particle again, except it still behaved like a wave sometimes. This is where the strangeness begins. Light is not a particle or a wave. It is both, or neither, or something else entirely that our words are not quite equipped to describe. When you set up an experiment to measure the wave properties of light, you find wave properties. When you set up an experiment to measure the particle properties of light, you find particle properties. It's as if light knows what you're looking for and decides to show you exactly that. This is called wave-particle duality. It is one of the central mysteries of modern physics, and it applies not just to light, but to everything: electrons, atoms, even large molecules. At very small scales, the universe does not behave the way we expect. We are used to things being one thing or another. A baseball is a ball. A wave in the ocean is a wave. We do not expect the baseball to sometimes act like a ripple spreading across a pond. We do not expect the ocean wave to sometimes act like a solid object flying through the air. But light does both. It spreads and it particles. It interferes with itself like a wave, and it knocks electrons loose like a ball. You don't need to understand this fully. No one does. The physicists who study it every day still argue about what it means. Some say the wave is real and the particle is just how we detect it. Some say the particle is real and the wave is just a mathematical description. Some say both are real, existing together in a way we cannot visualize. The honest answer is that we don't know. Light does what light does, and our human categories, wave, particle, thing, are just not quite right for it. But let's leave the deep physics behind for now and think about something simpler. How fast does light travel? The answer is very, very fast. About 300,000 kilometers per second, or 186,000 miles per second, if that measure is more familiar to you. This number is not approximate. It has been measured with extraordinary precision. Light in a vacuum travels at exactly 299,792,458 meters per second. Scientists have agreed to define the meter itself based on this speed. 1 meter is the distance light travels in about 3 billionths of a second. At this speed, light could circle the Earth more than 7 times in a single second. It could reach the moon in a little over 1 second. It could reach the sun in about 8 minutes. These numbers are hard to grasp. They sound impressive in an abstract way, but they don't really feel real. Our brains evolved to understand the speeds of running animals and thrown rocks, not the speeds of electromagnetic radiation crossing the solar system. So let's try to make it more concrete. Right now, as you listen to this, light is arriving at your location from the sun. If the sun suddenly vanished, which it won't, so don't worry, you would not know for 8 minutes. For 8 minutes, the sky would look the same. The warmth would feel the same. Then, all at once, everything would go dark. This is strange to think about. We tend to imagine that what we see is what exists right now, in this moment. But it isn't. What we see is what existed when the light left. We see the past. For nearby objects, this delay is so small it doesn't matter. The light from your hand reaches your eyes in about a billionth of a second. The light from the moon takes about 1.3 seconds. The light from the sun takes about 8 minutes. But when you look at the stars, the delays get much longer. The nearest star to our sun is called Proxima Centauri. It is about 4 light years away. This means the light you see from that star tonight left over 4 years ago. You are not seeing the star as it is now. You are seeing it as it was before the most recent presidential election, before the most recent Olympics, before whatever major events happened in the last 4 years of your life. And Proxima Centauri is close. Most of the stars you can see with your eyes are much farther away. Polaris, the North Star, is about 430 light years away. The light arriving from Polaris tonight left around the year 1590. Shakespeare had not yet written most of his plays. The telescope had not been invented. The light that is entering your eyes right now began its journey in a world that no longer exists. And this is just within our own galaxy. The Andromeda Galaxy, which you can sometimes see as a faint smudge in the night sky, is about 2.5 million light-years away. The light from Andromeda has been traveling since before modern humans existed. It left when our ancestors were still learning to chip stones into tools. When you look at Andromeda, you are looking at the deep past. You are seeing a galaxy as it was millions of years ago. What it looks like now, no one knows. The light showing us its current state won't arrive for another 2.5 million years. There is something almost dreamlike about this. The night sky is not a picture of the present. It is a mosaic of different times, different eras, all arriving at once. The nearby stars show you a few years ago. The distant stars show you centuries ago. The galaxies show you millions or billions of years ago. When astronomers point their telescopes, the most distant objects they can find, they are looking back toward the beginning of the universe. The light they capture has been traveling for over 13 billion years. It shows them what things looked like when the first galaxies were forming, when the universe was young and small and hot. This is not science fiction. This is just geometry and the speed of light. And it raises an interesting question. If everything we see is the past, what does the present even look like? The answer is, we don't know, we can never know. By the time light reaches us from anything, that thing has already changed. The present is always invisible. Let's slow down for a moment. You might be lying somewhere comfortable. The room might be dark. Your breathing might be settling into a slower rhythm. That is good. There is nowhere you need to be, nothing you need to do. These words will keep going, and you can listen or not, follow along or drift away. Light is a gentle subject. It does not demand urgency. It has been doing what it does for billions of years. A few more hours of quiet contemplation won't change anything. So take a breath if you'd like. Let your shoulders relax if they're tense, and we'll continue slowly whenever you're ready. We've talked about what light is and how fast it travels. Now let's think about what happens when light meets something. Most of the time, light travels in straight lines. In the emptiness of space, where there is nothing to interfere with it, a beam of light will go on forever, unchanging, undimmed, unless it runs into something. But light rarely has a clear path. There are atoms and molecules everywhere, dust, water, glass, air, and when light encounters these things, interesting things happen. Sometimes light bounces. This is called reflection. A mirror is a good example. The light hits the smooth surface and bounces back at the same angle it arrived. This is why you can see yourself in a mirror. The light from your face travels to the mirror, bounces, and returns to your eyes. But reflection doesn't require a mirror. Any surface reflects some light. The walls of your room, the floor, your own skin, everything that isn't perfectly black is sending some light back into the world. This is how we see objects. They don't generate their own light. They reflect light that comes from somewhere else. Sometimes light passes through. This is called transmission. Glass is transparent because it allows most visible light to pass through without absorbing it. Water is similar. Air is almost perfectly transparent to visible light, which is why you can see across a room or across a valley. But here's where it gets interesting. When light passes from one material to another, say, from air into glass, it changes direction slightly. It bends. This bending is called refraction. Refraction is responsible for some of the most beautiful effects in the natural world. Think of a straw in a glass of water. If you look at it from the side, the straw appears to be broken or bent at the point where it enters the water. It isn't actually bent, of course. It's an optical illusion created by refraction. The light coming from the part of the straw underwater travels through the water, then through the glass, then through the air, and finally into your eye. At each boundary, the light bends a little. By the time it reaches you, the light rays are coming from a different direction than you expect. Your brain interprets this as the straw being in a different position than it actually is. This same principle explains why pools look shallower than they are. The light from the bottom of the pool bends as it leaves the water, making the bottom appear closer to the surface. It also explains something far more spectacular: rainbows. A rainbow is one of those things that is both completely ordinary and completely magical. Ordinary because the physics behind it is straightforward. Magical because no matter how many times you see one, it still catches your breath. Here is what happens. Sunlight enters a raindrop. The raindrop is a tiny sphere of water suspended in the air. When the light enters, it slows down and bends. That's refraction. But sunlight is not a single color. It is a mixture of all the colors we can see, blended together so smoothly that it appears white. And here's the key: different colors bend by different amounts. Violet light bends the most. It has the shortest wavelength and slows down the most when it enters the water. Red light bends the least. It has the longest wavelength and doesn't slow down as much. So when white light enters a raindrop, it separates. The violet goes one way, the red goes another, and all the other colors, blue, green, yellow, orange, fan out in between. Then the light hits the back of the raindrop and reflects, bouncing back toward the front. As it exits the drop, it bends again, spreading the colors even further apart. What emerges is not white light anymore. It's a spray of colors fanning out at different angles. Now multiply this by millions of raindrops, all floating in the air after a storm. Each drop is sending out colors in slightly different directions. Your eye, standing in one spot, catches red light from the drops higher in the sky and violet light from the drops lower in the sky. The drops in between send you orange, yellow, green, blue. Put it all together and you see an arc of colors stretching across the sky, a rainbow. The rainbow you see is not in a fixed location. It's not an object you could walk toward and touch. It exists only in the relationship between the sun, the raindrops, and your eyes. If you moved, the rainbow would move with you. Each person standing in a field after a storm sees their own private rainbow, created by a different set of raindrops, sending light at exactly the right angle to reach their particular eyes. There is something quietly wonderful about this. The rainbow you see is yours alone. No one else sees exactly the same one. The spreading of white light into colors is called dispersion. You don't need raindrops to see it. A glass prism will do the same thing. So will the edge of a crystal. So will a thin film of oil on a puddle. Isaac Newton was the first to study this carefully. He took a beam of sunlight, passed it through a prism, and watched it spread into a band of colors on the wall. Then he took one of those colors, say green, and passed it through a second prism. It bent, but it didn't spread any further. Green stayed green. This told him something important. White light is not a single pure thing. It is a mixture. The prism doesn't add color to the light. It reveals the colors that were already there, hidden inside the white. The colors of the rainbow, red, orange, yellow, green, blue, violet, are called the visible spectrum. They represent the range of light that human eyes can detect. But here's the thing, the visible spectrum is tiny. Light, as we've said, is a kind of electromagnetic radiation. And electromagnetic radiation comes in a vast range of wavelengths, stretching from the very long to the very short. At the long end, you have radio waves. These have wavelengths measured in meters, sometimes kilometers. They carry radio broadcasts and television signals. They pass through walls as if the walls weren't there. Your body is bathed in radio waves right now, and you feel nothing, see nothing, notice nothing. A little shorter than radio waves are microwaves. These are used for radar and for cooking food. The microwave oven in your kitchen heats food by bombarding it with electromagnetic radiation at just the right wavelength to make water molecules vibrate. Shorter still is infrared. This is the range of wavelengths just below visible red. You can't see infrared, but you can feel it as heat. When you stand near a fire and feel warmth on your face, that warmth is infrared radiation. Then comes the visible spectrum: red, orange, yellow, green, blue, violet. This is the narrow band your eyes can detect. It spans wavelengths from about 700 nanometers, red, down to about 400 nanometers, violet. A nanometer is a billionth of a meter. The wavelengths of visible light are incredibly small, roughly the size of a virus. Just beyond violet is ultraviolet. You can't see it, but your skin responds to it. Ultraviolet light causes sunburns. It also causes certain materials to glow, which is why some white shirts look purple under black lights. Shorter than ultraviolet are X-rays. These can pass through soft tissue, which is why doctors use them to look at bones. They are energetic enough to be dangerous in large doses. And at the very short end are gamma rays. These are the most energetic form of electromagnetic radiation. They come from nuclear reactions and from the most violent events in the universe: supernovas, black holes, collisions of neutron stars. All of these radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays are fundamentally the same thing. They are all electromagnetic radiation. They all travel at the speed of light. They all consist of oscillating electric and magnetic fields. The only difference is wavelength, and wavelength determines everything: how the radiation interacts with matter, whether your eyes can see it, whether it can pass through walls or bones or lead. The visible spectrum, the rainbow, is just a tiny sliver of this vast range. If you imagine the full electromagnetic spectrum as a piano keyboard stretching from one end of a football field to the other, the visible spectrum would be about the width of a single key. We see such a small part of what is there. Why do we see this particular range? Why red to violet and nothing else? The answer lies in the sun. The sun emits radiation across a wide range of wavelengths, but it peaks in the visible range. Most of the sun's energy output falls between infrared and ultraviolet, with the maximum right in the middle of what we call visible light. Our eyes evolved to detect the wavelengths that were most abundant in our environment. This gave our ancestors an advantage. They could see predators, find food, navigate the world using the most available light. If we had evolved on a planet orbiting a cooler star, a star that emitted mostly infrared, our eyes might have been sensitive to infrared instead. We would see heat the way we see color. Our sunsets would look completely different. Our art and language would be built around wavelengths we can't even imagine. But we evolved here, under this sun, and so we see what we see. The narrow band of the rainbow is our window onto reality. Everything beyond it is invisible. Let's take a moment to let that settle. You are lying somewhere, perhaps in the dark, perhaps growing drowsy. The world around you is full of light you cannot see. Radio waves passing through your body, infrared radiating from your skin, ultraviolet blocked by the walls and windows. The universe is humming with electromagnetic energy, and you sense only a tiny fraction of it. This is not a failure of your senses, it is simply their nature. They evolved to detect what was useful, not what was complete. There is no shame in having limits. Every creature has them. Bees can see ultraviolet patterns on flowers that are invisible to us. Pit vipers can sense the infrared heat of their prey. Mantis shrimp have 16 different types of color receptors compared to our 3. Each species sees a different slice of reality. Each thinks its slice is the whole picture. We've been talking about light as something that exists outside us in the world. But of course, light only becomes meaningful when it enters a living eye and gets translated into experience. So let's spend some time now thinking about how we actually see. Your eye is a small, wet sphere about an inch across. At the front is a transparent layer called the cornea, which bends incoming light. Behind that is the iris, the colored part, which adjusts how much light gets in. In the center of the iris is the pupil, a dark hole that expands in dim light and contracts in bright light. Behind the pupil is the lens, a flexible structure that focuses light onto the back of the eye. And at the back of the eye is the retina, a thin layer of tissue covered in light-sensitive cells. These cells are called photoreceptors. They are the interface between the physical world of light and the mental world of vision. There are 2 main types of photoreceptors, rods and cones. Rods are extremely sensitive. They can detect even tiny amounts of light, just a few photons. This makes them perfect for seeing in dim conditions. When you walk outside on a moonlit night and can just barely make out the shapes of trees and fences, you are seeing with your rods. But rods have a limitation. They cannot detect color. They see only in shades of gray. This is why colors seem to fade when the light gets low. In near darkness, everything looks gray and muted. The human eye contains about 120 million rods, mostly concentrated around the edges of the retina. This is why you can sometimes see faint stars better if you look slightly to the side of them. You're putting their light on the part of your retina where the rods are densest. Cones are different. They are less sensitive, they need more light to work, but they can detect color. There are about 6 million cones in the human eye, concentrated in the center of the retina in a region called the fovea. When you look directly at something, you are aiming its light at your fovea, where the cones are packed tightest. This is why your central vision is sharp and colorful. Cones come in 3 types, each sensitive to a different range of wavelengths. One type responds most strongly to long wavelengths, which we perceive as red. Another responds to medium wavelengths, which we perceive as green. The third responds to short wavelengths, which we perceive as blue. By comparing the signals from these 3 types, your brain can construct the experience of color. A lemon reflects light that stimulates both the red and green cones, so your brain interprets it as yellow. A blueberry reflects light that stimulates mainly the blue cones, so your brain interprets it as blue. All the colors you see, every shade and hue in the entire visible world, are built from combinations of just 3 signals: red, green, and blue. Mix them in different proportions, and you get everything from pink to brown to aquamarine. This is a simplification, of course. The real process is far more complex. The signals from your cones pass through layers of neural processing before they ever reach the parts of your brain that handle conscious vision. Edges are sharpened, patterns are identified, context is considered. The color you perceive is not simply the wavelength of light hitting your eye. It depends on the surrounding colors, on your recent visual experience, on your expectations. 2 patches of light that are physically identical can look completely different if they are surrounded by different colors. Color is not in the world, it is in your head. Objects have no color of their own. They have surfaces that absorb certain wavelengths and reflect others. The wavelengths that reach your eye are just numbers, frequencies, and intensities. The experience of redness or blueness or greenness is something your brain adds. This is a subtle point, and it can feel a little unsettling. We tend to think of colors as real properties of objects, as if a fire truck is inherently red, as if that redness exists in the metal and paint. But a fire truck is not red. It reflects light at wavelengths around 700 nanometers. Your brain, receiving those wavelengths, generates the experience of redness. The red is in you, not in the truck. Let's pause here for a while. These are strange ideas, and they don't need to be grasped firmly. They can float around in your mind, settling wherever they settle. You may be getting drowsier now. The words may be blurring together slightly, becoming more of a texture than a sequence of meanings. That's fine. Let yourself drift if you want to drift. We'll keep going, but the pace will slow. The facts will become less urgent. The sentences will soften. There is a kind of light that comes from very far away. When you look at the stars, most of what you see is light from fusion, deep inside each star. Hydrogen atoms are being crushed together under unimaginable pressure, fusing into helium. This process releases energy, a lot of energy. Some of it radiates outward as light. The sun is doing this right now, every second of every day. 600 million tons of hydrogen are being converted into helium in the sun's core at this very moment. The energy released by this process is what keeps the sun shining. It has been shining like this for about 4.5 billion years. The light leaving the sun's surface is what we see as sunlight, but that light didn't start its journey at the surface. It started deep inside the core where the fusion happens. And here's something remarkable. That light, or rather the energy that became that light, might have taken 100,000 years or more to reach the surface. Inside the sun, things are extremely dense. The core is packed with charged particles, protons and electrons and other bits of matter, all jostling against each other. When a photon is created in the core, it doesn't just fly straight outward. It travels a tiny distance, then gets absorbed by a particle. That particle emits another photon, which travels a tiny distance and gets absorbed again. This process repeats over and over. Each photon takes a random step, bounces, gets absorbed, gets emitted. It's like trying to walk across a crowded room where everyone is bumping into you from all sides. This random walk takes a long time. Some estimates suggest the energy from the core takes between 10,000 and 170,000 years to work its way to the surface. The numbers vary depending on who's doing the calculation and what assumptions they make. But the point is clear. The sunlight we see today was generated deep inside the sun long before human civilization existed. Once that energy finally reaches the surface, though, everything changes. The outer layers of the sun are much less dense. Photons can escape. They fly outward into space at the speed of light, and in just 8 minutes, they cross the 93 million miles to Earth. So the sunlight touching you right now is ancient and new at the same time. Ancient in its origin, new in its arrival. Light carries energy. This is not a metaphor. It is a physical fact. A photon is a packet of energy, and when it is absorbed by something, that energy is transferred. This is why sunlight feels warm. When photons hit your skin, some of them are absorbed. Their energy becomes heat in your body. This is also why sunlight can cause sunburn. Ultraviolet photons carry more energy than visible light photons. When they are absorbed by your skin cells, they can damage DNA. Your body's response to this damage is what we call a sunburn. And this is why sunlight makes life possible. Plants have figured out how to capture the energy in light and store it as chemical energy. This process is called photosynthesis. Inside the cells of a leaf are tiny structures called chloroplasts. Inside the chloroplasts is a green pigment called chlorophyll. When light hits chlorophyll, it excites electrons in the molecule, boosting them to a higher energy state. This excited energy is then passed along through a chain of chemical reactions. Water molecules are split apart, releasing oxygen as a waste product. Carbon dioxide molecules from the air are captured and combined with other molecules. Eventually, the energy ends up stored in the bonds of a sugar molecule called glucose. The glucose can be used later for energy. It can be converted into other molecules the plant needs. It can be stored as starch. And when you eat a plant, or when you eat an animal that ate plants, you are eating stored sunlight. The energy that keeps your body running came from photons that left the sun, crossed millions of miles of space, and were captured by chlorophyll in a leaf somewhere. Every breath you take, every movement of your muscles, every thought flickering through your brain, all of it is powered by ancient starlight. This is one of those facts that seems almost too poetic to be true, but it is true. The economy of life on Earth is fundamentally a solar economy. Energy flows from the sun to plants to animals to decomposers and back into the soil and air, cycling and recycling, but always originating in that same source, the nuclear fusion reactions at the heart of our star. Take away the sun and this whole system collapses. Photosynthesis stops, plants die, animals follow. The food chain unravels from the bottom up. We don't think about this often because we don't have to. The sun has been reliable for all of human history and for billions of years before that. It will continue to be reliable for billions of years more. But it is worth pausing now and then to appreciate how much depends on that steady stream of photons. The light around you right now, whatever faint glow is illuminating your space, is a continuation of this ancient process. If it's electric light, the electricity probably came from burning fossil fuels, which are the compressed remains of ancient plants and animals, which got their energy from ancient sunlight. Or maybe it came from solar panels, capturing sunlight directly, or from wind turbines, which are powered by air currents driven by solar heating. Or from hydroelectric dams, which capture water that was lifted into the sky by solar evaporation. Almost every form of energy we use traces back to the sun. The exceptions, nuclear power, geothermal energy, are interesting precisely because they don't, but they are the minority. For most of human history, light meant fire. People burned wood, then oil, then coal, then gas. They captured and released ancient sunlight in controlled bursts. The flames in a fireplace are a kind of time-delayed solar energy, stored for millennia and released in a single evening. Now we have electric lights, which transform energy from distant sources into visible radiation. The light from a bulb is not sunlight, but the energy behind it usually is, one way or another. Let's let the mind wander now. There is no need to follow a strict thread. The night is long, and the facts don't need to march in formation. Let them drift. Think about the color of fire. The blue at the base of a candle flame, where the burning is hottest. The yellow and orange higher up, where it's cooler. The red at the very tips, barely visible. Fire glows because it's hot, and hot things emit light. The color tells you the temperature. This is true of stars, too. Blue stars are hotter than white stars. White stars are hotter than yellow stars. Yellow stars are hotter than orange stars. Orange stars are hotter than red stars. Our sun is a yellow star, medium temperature, medium brightness, ordinary, really. There are billions of stars like it in our galaxy alone. When you look at the night sky with your naked eye, almost everything you see is a star. A few dots are planets, Jupiter, Saturn, Mars, Venus, reflecting sunlight back at you. But the vast majority are distant suns, burning through their nuclear fuel, shining their light across the void. Some of those stars have planets orbiting them. We've discovered thousands of such planets in recent decades, using telescopes that can detect the faint dimming of a star when a planet passes in front of it. Some of those planets are rocky, like Earth. Some are in the habitable zone, where liquid water might exist. We don't know if any of them have life. We don't know if any of them have beings who look up at their own sky and wonder about the universe. But the possibility is real. Light from those worlds is traveling through space right now. If there is anyone there to send it, or even if there isn't, the photons don't care. They travel regardless. There's a certain comfort in the steadiness of light. It doesn't hurry, it doesn't slow down, it doesn't get tired. A photon created in a distant star will travel at the same speed for 1 billion years, unchanging, until it is absorbed by something. In a universe full of change, stars being born, stars dying, galaxies colliding, species evolving and going extinct, light is a constant. The speed of light is built into the structure of space and time. It is the fastest speed at which anything can travel, and it is the same everywhere for everyone. This is not obvious. You might think that if you were moving very fast toward a beam of light, the light would seem to be coming at you faster, but it doesn't. No matter how fast you move, light always arrives at the same speed. This was Einstein's great insight, the foundation of his theory of relativity. It leads to strange consequences. Time slows down as you approach the speed of light. Lengths contract, mass increases. The faster you go, the more warped the universe becomes around you, but the speed of light remains the same. There's a kind of reassurance in that. Amid all the strangeness of the relativistic world, light holds steady. It is the fixed point around which everything else bends. Let your breathing slow if it hasn't already. Let your thoughts loosen their grip on the facts. Light is still there, whether you think about it or not. It will keep traveling, keep bouncing, keep being absorbed and re-emitted. The sun will rise in a few hours, flooding the world with photons. The stars will keep shining, though you won't see them in the daylight. For now, rest. There is a quality of light in the early morning that is different from any other time. Just before dawn, when the sky is still dark but beginning to lighten at the edges, the light is soft and directionless. It seems to come from everywhere at once. Shadows are vague and muted. Colors are desaturated, as if the world hasn't fully woken up yet. Then the sun crests the horizon and everything changes. Suddenly there is a source. Shadows snap into focus. colors warm, the world becomes three-dimensional again with highlights and depths. This transition from diffuse twilight to direct sunlight happens every morning, everywhere on Earth. It has happened every morning for billions of years, and yet, if you're awake to see it, it can still feel like a small miracle. We don't often watch the sunrise anymore. We have screens and schedules and indoor lives. The sun rises whether we see it or not. But there was a time when the sunrise was the most important event of the day. It told you when to wake, when to work, when to hunt, when to rest. Human circadian rhythms are built around the cycle of light and dark. Our bodies expect the sun. Even now, exposure to morning light helps regulate your sleep-wake cycle. It suppresses melatonin, the hormone that makes you drowsy. It tells your internal clock that the day has begun. And exposure to dim light in the evening tells your body that night is coming. Melatonin rises, alertness fades, sleep approaches. You may be feeling some of that now. The words have become a kind of dim light, getting you toward rest. There's no need to resist it. Sleep is not something to fight against. It is something to move toward, gently, like walking down a slowly darkening hallway. The facts about light don't need to be held in your memory. They can fade like colors at dusk, settling into the background. What matters now is not knowing but resting. Let's think about shadows for a moment. A shadow is a place where light doesn't reach. It's an absence, a gap in the illumination. But we tend to think of shadows as things themselves, as dark shapes with edges and substance. A tree casts a shadow. A building casts a shadow. Your own body casts a shadow when you stand in the sun. Shadows move as the light source moves. Throughout the day, the sun traces an arc across the sky, and every shadow shifts in response, swinging around like the hands of a slow clock. Before there were clocks, people told time by shadows. A stick planted in the ground, called a gnomon, would cast a shadow that moved predictably with the sun. This was the basis of the sundial, one of the oldest timekeeping devices. There is something peaceful about telling time by light. It connects you to the sky, to the movement of the earth, to the slow rotation that carries you from day to night and back again. Shadows are softer when the light source is large. On a cloudy day, when the sun is hidden behind a uniform layer of white, shadows almost disappear. The light comes from the entire sky, not from a single point. It arrives from many directions at once, filling in the gaps, erasing the sharp edges. Photographers call this diffuse light. It's flattering for portraits because it doesn't create harsh shadows on the face. It's calming for the eyes because there are no stark contrasts. Moonlit nights have soft shadows too. The moon is bright enough to see by, but not bright enough to create sharp edges. Everything looks gentler under moonlight. Think about moonlight for a moment. The moon produces no light of its own. It is just a ball of rock orbiting the earth, reflecting whatever sunlight falls on it. When you see the moon in the night sky, you are seeing sunlight that has bounced off the lunar surface and traveled to your eyes. This is second-hand light. It is weaker than direct sunlight, about 400,000 times weaker, but it is still enough to see by. On a clear night with a full moon, you can walk outside without a flashlight. You can see the shapes of trees, the outlines of buildings, the texture of the ground. Moonlight is blue-gray. This is partly because of the color of the lunar surface and partly because of how your eyes work in low light. In dim conditions, your rods take over from your cones, and rods are more sensitive to shorter wavelengths. So moonlight looks cooler, bluer, even though it's really just reflected sunlight. There's a dreamy quality to moonlit nights. The world looks different, quieter, softer, stranger. It's the same world you see in daylight, but transformed by the change in light. We are creatures of light. Our lives are shaped by it. Our moods are influenced by it. Our bodies are regulated by it. Bright days make us alert. Dim evenings make us sleepy. Sunny climates tend toward one kind of temperament, cloudy climates toward another. This is not determinism. We are not puppets of the light, but we are sensitive to it more than we usually realize. A room with good natural light feels different from a room with none. A city full of neon and streetlights feels different from a village lit only by stars. The quality of light in a place becomes part of its character. If you've ever traveled far, you may have noticed how the light is different in different parts of the world. Near the equator, the sun is high and strong. Shadows are short at midday, almost directly underfoot. The light is intense, even harsh. In northern latitudes, the sun stays lower in the sky. Even at noon in winter, the light comes in at an angle. Shadows are long and slanted. The light is softer, more golden. Artists have always known this. The light in Italian Renaissance paintings is different from the light in Dutch paintings. The light in California photography is different from the light in Scandinavian film. Each place has its own quality, its own palette, shaped by the angle of the sun. There's a time of day that photographers and cinematographers call the golden hour. It's the hour just after sunrise and the hour just before sunset, when the sun is low and the light is warm and soft. During the golden hour, everything looks beautiful. Skin glows, landscapes shimmer, ordinary scenes become magical. This is partly because of the color of the light. When the sun is low, its rays pass through more of the atmosphere before reaching you. The blue wavelengths scatter away, leaving mostly red and orange. Everything is bathed in warm tones. And it's partly because of the angle. Low-angle light creates long shadows and highlights textures. Surfaces that look flat at noon become three-dimensional at sunrise or sunset. People have always loved this light. It appears in countless paintings, photographs, films. It is the light of romance and nostalgia, of endings and beginnings. There's another time of day, less celebrated but equally beautiful. Photographers call it the blue hour. It's the period just before sunrise and just after sunset, when the sun is below the horizon, but its light is still scattering in the atmosphere. During the blue hour, the sky is a deep, saturated blue, and the light on the land is cool and even. There's no sun to cast direct shadows, so everything is softly illuminated. The blue hour is quiet. It feels like a threshold, a moment between states. Night is ending or night is beginning, and the world is holding its breath. Let yourself settle into that kind of light if you can. Imagine a soft blue dusk, no sun, no harsh shadows. The world is calm, the air is still, nothing is required of you. You can let the words wash over you now. They don't need to stick. They can pass through like light through a window, leaving only a gentle warmth. We've covered a lot of ground, and we've done it slowly. We've talked about what light is, wave, particle, both at once. We've talked about how fast it travels, fast enough to circle the Earth 7 times in a second, yet slow enough that we see the stars as they were years or millennia ago. We've talked about refraction and rainbows, about the electromagnetic spectrum and the narrow band we can see. We've talked about rods and cones, about how color is not in the world, but in our minds. We've talked about photosynthesis and how all life on Earth runs on stored sunlight. We've talked about shadows and the golden hour, about moonlight and the blue hour. None of these are urgent truths. They are just features of the world, aspects of the light that has been shining since long before you were born and will continue shining long after. There is a kind of peace in that. The universe does not need your attention. The sun will rise whether you see it or not. The stars will shine whether anyone is looking. You are a small piece of a very large system, and the system hums along regardless. This can feel lonely, but it can also feel freeing. You don't have to hold it all up. You don't have to keep it going. It goes by itself. Let your body grow heavy now. Let your mind grow quiet. The light outside your room will do what it does. The photons will travel. The waves will oscillate. The colors will scatter and absorb and reflect. And you, here in the dark, can rest. Sleep is a little like darkness. It's an absence, a gap, a space where waking light doesn't reach. But sleep is not nothing. Your brain is still active, cycling through stages of rest and dreaming. Your body is still working, repairing and restoring. Sleep is its own kind of life, different from waking life, but not less real. In sleep, you are still part of the world, still breathing the air, still warmed by the heat around you, still affected by the light, even if your eyes are closed. Morning will come, and light will return, and you will wake into another day. But that's later, that's not now. Now is for rest. Let the words fade. Let the facts dissolve. Let the quiet complexity of light be what it is, quiet, complex, always there, and let yourself drift away from it into the soft darkness of sleep. There's nothing else you need to do. Nothing you need to remember. Nothing you need to figure out. Just rest. The light will wait. It always does. And so we continue gently. You may still be awake. You may be drifting somewhere between waking and sleep, where the words arrive but don't quite land, where the meaning floats just out of reach. Either way is fine. There is no right way to be here. The room around you is probably dark or close to it. Maybe there's a faint glow from somewhere, a streetlight through the curtains, the dim pulse of a charging device, the soft luminescence of a clock. These small lights are enough to remind you that even in darkness, light is never fully absent. We were talking about light. We covered the big ideas, what it is, how fast it travels, how we see it, how it bends and separates into colors. Now let's wander a bit. Let's follow some quieter threads, without hurry, without destination. Think about the inside of your eyelids. When you close your eyes, you don't see pure black. You see a kind of reddish darkness, especially if there's any light in the room. This is because your eyelids are thin enough that some light passes through. The red color comes from the blood vessels in the tissue. If you press gently on your closed eyes, not hard, just a light touch, you might see strange patterns, swirls of color, geometric shapes, sparks of light that seem to come from nowhere. These are called phosphenes. They're not real light. They're your visual system responding to pressure, generating signals that your brain interprets as light even though no photons are involved. Your eyes are so sensitive, so eager to see, that they can create the sensation of light from nothing at all. This happens in total darkness too. If you've ever been in a cave deep underground, where no light from the outside world can reach, you know that even there, your eyes don't give up. After a while, you start to see faint glimmers, patches of gray, floating shapes. This is neural noise, random signals in your visual system that your brain tries to interpret as something meaningful. We are built to see. Even when there's nothing to see, we try. Let's think about darkness itself for a while. Darkness is not a thing. It is the absence of light. You cannot shine darkness the way you shine a flashlight. You cannot collect darkness in a jar. It has no substance, no particles, no waves. It is simply what remains when light is taken away. And yet darkness feels real. It has weight and texture. A dark room feels different from a bright one. A dark night feels different from a dim evening. Darkness presses in, creates intimacy, encourages rest. Our ancestors feared the dark. In darkness, predators could approach unseen. In darkness, dangers were invisible. The night was full of threats that could not be faced directly. So humans learned to make fire, to push back the darkness, to create islands of light in the black sea of night. But darkness is not only danger, it is also rest. It is also mystery. It is also the time when the stars come out. The stars are only visible because of darkness. During the day, the stars are still there. They don't go anywhere. But the sky is flooded with sunlight, scattered by the atmosphere into the blue dome we see overhead. That scattered light is so much brighter than starlight that it drowns the stars out completely. At night, the sun drops below the horizon and the scattered light fades. The sky darkens and suddenly the stars appear, as if someone had turned on 1,000 tiny lamps. They were always there, we just couldn't see them. This is true of many things. The world is full of phenomena that are present but invisible, hidden by brighter signals or by the limitations of our senses. Ultraviolet light is always around us, but we can't see it. Radio waves are passing through your body right now, carrying music and conversations and data, but you perceive none of it. Our experience of reality is filtered, simplified, reduced to the narrow band that our senses can detect. What we call the world is really just the small slice of the world that our eyes and ears and skin can pick up. This is not a flaw, it's a feature. If you could perceive everything, every wavelength of light, every frequency of sound, every subtle vibration, you would be overwhelmed. The filtering is necessary. It allows you to focus on what matters, to navigate the environment, to survive. But it's worth remembering, now and then, that there's more out there than you can see. The universe is richer than your senses suggest. Let that thought rest lightly. You don't need to grasp it firmly or understand it fully. It's just a perspective, a way of looking at things. The world is large and strange, and you are a small creature with limited senses, and that's okay. That's just how it is. Let's return to something simpler. Think about a candle flame. If you've ever watched a candle burn, you know how hypnotic it can be. The flame dances and flickers, never quite still, responding to currents of air too subtle to feel. It changes color as it moves, blue at the base, yellow in the middle, orange at the tips. The blue part is the hottest. That's where the wax vapor is mixing with oxygen and combusting most completely. The yellow and orange parts are cooler. They contain tiny particles of unburned carbon glowing from the heat. These particles are what make the flame luminous. A candle flame is a small, controlled fire. It's burning at perhaps 1,000 degrees Celsius, hot enough to melt metal, and yet it sits calmly on your table, contained by nothing but air. Fire was humanity's first artificial light. For hundreds of thousands of years, fire was the only way to see in the dark. Torches, oil lamps, candles, lanterns, all variations on the same basic principle. Take something that burns, set it alight, and it will glow. The light from fire is warm in color, rich in red and orange and yellow wavelengths. This is because fire is not as hot as the sun. Cooler objects emit longer wavelengths when they glow. The sun, at about 5,500 degrees Celsius, emits light across the visible spectrum, which we perceive as white. A candle flame, much cooler, emits light skewed toward the red end. Our ancestors spent countless evenings gathered around fires, staring into the flames, talking, telling stories, preparing for sleep. The flickering light was their companion, their protection against the dark. There is something deeply calming about firelight. Researchers have studied this. When people watch a fire, even a video of a fire, their blood pressure tends to drop. Their muscles relax, their minds quiet. This makes evolutionary sense. For most of human history, a fire meant safety. It meant warmth. It meant the predators would stay away. A fire was a signal that all was well, that the dangerous night had been tamed. We still respond to that signal, even though we no longer need fires to survive. A fireplace in a living room, a campfire on a beach, even a candle on a dinner table, all of them trigger some ancient part of the brain that says, "Rest now, you are safe." You don't have a fire in front of you now, probably. But you can imagine one if you like, a small flame. Steady and warm, casting a soft glow on the walls around you. The gentle crackle of burning wood, the smell of smoke, faint and pleasant. Let that image settle in your mind if it helps, or let it go if it doesn't. There's no right way to do this. We've been talking for a while now. The words have been accumulating, one after another, building a kind of structure in the dark. But structures don't need to hold together perfectly. They can be loose, provisional, easily forgotten. The point is not to remember. The point is to be here, in this moment, with these sounds, and to let them carry you somewhere restful. Let's think about the color blue. Blue is a curious color. It's the color of the sky during the day, the color of deep water, the color of certain flowers and birds and butterflies. It's often associated with calm, with distance, with melancholy. The sky is blue because of something called Rayleigh scattering. When sunlight enters the atmosphere, it collides with molecules of nitrogen and oxygen. These collisions scatter the light in all directions, but they scatter shorter wavelengths more than longer ones. Blue light, with its short wavelength, gets scattered much more than red or yellow light. So when you look at the sky, not at the sun itself, but at any other part of the sky, you're seeing blue light that has been scattered toward you from all over the atmosphere. The sky is glowing with redirected blue. At sunrise and sunset, the light has to pass through more atmosphere to reach you. More of the blue gets scattered away before it arrives, leaving the longer wavelengths, red and orange, to dominate. This is why sunsets are warm and skies at noon are blue. The ocean looks blue for a different reason. Water absorbs light, but it doesn't absorb all wavelengths equally. It absorbs red light more than blue light. So when you look at deep water, the red wavelengths have been absorbed, and what remains is blue. This is also why underwater scenes in movies often have that blue-green tint. It's not just artistic choice, it's physics. The deeper you go, the more red light gets absorbed, and the bluer everything looks. At the very deepest parts of the ocean, there is no light at all. The sunlight has been absorbed completely. It's dark down there, as dark as outer space. The creatures that live in the deep have no use for eyes, or they've developed other ways of seeing: bioluminescence, sensitive pressure detectors, chemical sensors. Bioluminescence is light produced by living things. Fireflies do it, so do many deep-sea creatures, fish, squid, jellyfish. They produce light through chemical reactions, without heat, without fire. The light is usually blue or green because those wavelengths travel farthest through water. A deep-sea fish with a red light would be almost invisible because there's no red light at that depth for comparison. But a blue light stands out, a beacon in the darkness. Some creatures use bioluminescence to attract mates. Some use it to lure prey. Some use it to startle predators. Some use it for communication, flashing patterns to each other in the dark. There's something magical about bioluminescence. Light without fire, without electricity, without the sun. Just chemistry performing its quiet miracle in the bodies of living things. You are not bioluminescent, but your body does glow very faintly. All warm objects emit some electromagnetic radiation. For objects at human body temperature, this radiation is mostly infrared, wavelengths too long for your eyes to see, but a tiny, tiny amount falls in the visible range. Scientists have measured this. Human skin emits about 1,000 photons of visible light per square centimeter per second. This is far too faint to see with the naked eye, about 1,000 times weaker than what your eyes can detect, but it's there. You are glowing, right now, with a light so faint it might as well be invisible. A dim, warm radiance coming from the chemistry of your cells. Let that thought be a comfort, if you like. Even in total darkness, you are not entirely dark. Even alone, you are producing your own tiny light. It's not much, it's not enough to see by, but it's something, a small glow in the void. The night is deepening now, in the world outside your window or inside your mind. The words are slowing down, the pauses are growing longer, there is less urgency with each passing minute. This is as it should be. Sleep approaches not with fanfare but with quiet. It doesn't announce itself. It seeps in, gradually, like water soaking into sand. Let's think about the moon again. The moon is a constant companion, though we don't always notice it. It rises and sets on its own schedule, sometimes visible during the day, sometimes only at night, sometimes not at all when it's in its new phase. The phases of the moon are caused by the geometry of Sun, Earth, and Moon. As the moon orbits the Earth, different portions of its lit surface are visible to us. When the moon is between the Earth and the Sun, we see only its dark side. This is the new moon. When the Earth is between the moon and the Sun, we see the fully lit side. This is the full moon. In between, we see crescents and quarters and gibbous shapes. The same side of the moon always faces the Earth. This is because the moon's rotation is synchronized with its orbit. It spins exactly once for every trip around our planet. This is called tidal locking. It's not a coincidence. It's a result of gravitational forces over billions of years. So when you look at the moon, you're always seeing the same craters, the same dark patches, the same features that humans have gazed at for all of history. The far side of the moon was a mystery until spacecraft flew around to photograph it in the 1950s. The moon has no atmosphere, no weather, no wind. The footprints left by astronauts in the 1960s and 70s are still there, undisturbed, preserved in the lunar dust. Those footprints will likely remain for millions of years. Without wind or water to erode them, they have only micrometeorites to worry about, and those are rare. Future visitors to the moon will find them waiting, a monument to human curiosity. The moon is slowly drifting away from the Earth. Each year, it moves about 3.8 centimeters farther away. This is because the tides that the moon raises on Earth are slightly ahead of the moon's position, and they pull the moon forward, giving it energy, pushing it into a higher orbit. 3.5 billion years ago, the moon was much closer, perhaps only about 15,000 miles away, compared to about 240,000 miles today. It would have looked huge in the sky, dominating the view, raising enormous tides. In the distant future, the moon will be so far away that total solar eclipses will no longer be possible. The moon's disk, as seen from Earth, will be too small to cover the sun completely. This won't happen for hundreds of millions of years, but it will happen eventually. Eclipses are strange and beautiful events. A solar eclipse happens when the moon passes directly between the Earth and the sun, blocking the sun's light. This can only happen during a new moon, and only when the moon's orbit crosses the plane of Earth's orbit at just the right moment. During a total solar eclipse, the sky goes dark in the middle of the day. Stars become visible, animals behave as if night has fallen, the temperature drops, and around the blocked sun, you can see the corona, the sun's outer atmosphere, a wispy halo of plasma that is usually invisible in the sun's glare. People have traveled thousands of miles to witness total solar eclipses. There's something primal about them, something that stirs deep emotions. For a few minutes, the normal order of the world is suspended. The sun disappears, darkness falls, and then the light returns and everything goes back to normal. A lunar eclipse is quieter but still beautiful. It happens when the Earth passes between the sun and the moon, casting its shadow on the lunar surface. The moon doesn't go completely dark. Some sunlight bends around the Earth's atmosphere and reaches the moon, giving it a reddish glow. This is sometimes called a blood moon. The red color comes from the same physics that makes sunsets red. Earth's atmosphere scatters away the blue light and allows the red light to pass through. The moon, sitting in Earth's shadow, is lit by all the sunrises and sunsets happening around the rim of the Earth at that moment. If you were standing on the moon during a lunar eclipse, you would see the Earth as a dark circle surrounded by a glowing red ring, the light of all the sunrises and sunsets on Earth, all at once. There is a patience to astronomical events. They happen on their own schedule, indifferent to human concerns. Eclipses come and go whether anyone watches or not. The stars wheel overhead whether anyone looks up or not. The universe proceeds according to its own laws, vast and slow and unconcerned. This can feel humbling or it can feel peaceful. We are small and the universe is large, and neither of those facts is good or bad. They just are. Let's slow down even more now. The facts have been piling up, and they don't all need to stay. Let them scatter like leaves. Let them drift away like clouds. What remains is simpler. Light exists. It travels. It touches things. It makes the world visible. It enables life. And right now, in this moment, you are resting in darkness, letting the light wait until morning. Think about your breaths. You don't have to change it. Just notice it if you can. The air coming in, the air going out. The gentle rise and fall of your chest or belly. Breathing is automatic. You do it without thinking, thousands of times a day, tens of thousands of breaths, keeping you alive without any effort on your part. The oxygen in that air came from somewhere. Most of it came from photosynthesis, plants splitting water molecules and releasing oxygen as a byproduct. Every breath you take connects you to the green world, to the forests and fields and algae of the ocean, all of them working quietly, capturing sunlight, releasing the gas you need to survive. You are breathing ancient sunlight in a way. The energy that split those water molecules came from photons. The photons came from the sun. The sun has been shining for billions of years. There's a cycle here, a loop that connects everything. The sun shines, plants capture the light, oxygen is released, animals breathe the oxygen, animals eat the plants. Energy flows from sun to plant to animal and back into the air and soil. You are part of this cycle. Your body is made of atoms that have been cycled and recycled through countless living things over billions of years. The carbon in your bones was once in the ocean, in the soil, in the bodies of dinosaurs and ferns and bacteria. Nothing is truly separate. Everything is connected through light and air and water and time. This is not a spiritual claim, though it can feel spiritual. It's just biology and chemistry and physics doing what they do. But the facts themselves are remarkable enough. You don't need to add anything mystical to find wonder in them. Let's let the facts fade now. The connections are there whether you think about them or not. The cycles continue whether you pay attention or not. The light keeps traveling, the plants keep breathing, the stars keep shining. You can rest. Imagine a quiet room. The walls are soft and neutral. The air is still. There is no sound or almost no sound, just the faint hum of the world continuing outside. In this room, there is a window. The curtains are drawn, but a little light comes through. Not enough to see by, just enough to know that the outside world exists. You are lying down, your body is heavy and relaxed, your thoughts are slow and distant. Nothing is required of you, nothing is expected. You are simply here in this quiet room resting. The light that filters through the curtains is old light. If it's moonlight, it left the sun about 8 minutes before it hit the moon, and then another 1.3 seconds to reach you. If it's starlight, it may have traveled for years or centuries or longer. Even the light from a street lamp carries a history. The electricity that powers it was generated somewhere, a power plant, a solar panel, a wind turbine. The energy in that electricity came from somewhere else, burning fuel, sunlight, wind currents caused by solar heating. Every photon that reaches you is the end of a long chain of events. It carries information about where it has been, what it has touched, what has happened to it along the way. But you don't need to trace those chains. You can just let the light be what it is, a faint glow, a presence in the dark. Sleep is getting closer now. You can feel it maybe, a heaviness in your limbs, a softening of your thoughts, the world receding, becoming less urgent, less real. This is the natural rhythm, light and dark, waking and sleeping, activity and rest. You've been awake for a while. Your body has done its work. Now it's time to let go, to surrender to the darkness, to trust that the light will return when it's time. Let the words become a murmur. Let the sentences blur. Let the meaning dissolve. There's a light inside you too. Not literally, not enough to see by, but metaphorically, there's something that keeps going, some spark that animates your body and mind. Call it consciousness, call it life, call it whatever you like. That light doesn't need to stay bright right now. It can dim for a while, it can rest, it will still be there in the morning. The universe is full of light and darkness, activity and stillness, noise and silence. Right now somewhere, a star is being born. Gravity is pulling gas and dust together, squeezing it, heating it, until fusion ignites and light pours out. Right now somewhere else, a star is dying. It has burned through its fuel and is collapsing or exploding or fading into a dim ember. Right now on Earth, millions of people are awake, working, talking, moving through their days, and millions of others are asleep, like you are becoming, resting in the dark. It all happens at once. The universe doesn't wait, it doesn't pause. It keeps going in all directions, at all scales, in all places. But you don't have to keep up with it. You can step out of the stream for a while. You can rest on the bank and let the water flow past. The light will be there when you return. The sun will rise, the world will brighten, colors will return, shadows will sharpen. But that's later, that's not now. Now is for quiet. Now is for darkness. Now is for sleep. Let yourself go. Let your body sink into whatever surface holds you. Let your breath slow. Let your thoughts scatter like starlight, spreading out into the dark. There is nothing else. Just this moment. Just this rest. Just the quiet complexity of light, waiting patiently for you to return. Sleep now. The light will wait. It always does. And if you're still here, still awake, still listening, that's fine too. There's no failure in wakefulness. Sleep comes when it comes. Sometimes it takes longer. Sometimes the mind needs more time to quiet down. Let's keep going then, gently, slowly, without any pressure. Think about the color of early morning. Before the sun rises, the sky begins to lighten. It starts in the east, a faint glow on the horizon. The stars fade, one by one, as the scattered light of the approaching sun fills the sky. The first colors are gray and pale blue, then pink appears, sometimes orange. The clouds catch the light and glow from within. And then the sun crests the horizon and everything changes. The world floods with light, colors intensify, the day begins. There's a promise in every sunrise. Not a guarantee, but an invitation. A new day, a fresh start, another chance. Humans have been watching sunrises for as long as there have been humans. We've built monuments to mark them. Stonehenge, Newgrange, temples aligned to catch the first rays. We've written poems and songs and stories about them. The sunrise means survival. It means warmth. It means the night is over and the world is safe again. But right now, the sunrise is far away. Hours away, probably. The night is deep and the darkness is complete. The world is quiet and you are resting. Let the sunrise wait. It knows how to find you. It will come when it's time. Think about something pleasant. Not something exciting or stimulating, something soft, something calm. Maybe a place you've been where you felt at peace. A beach, a forest, a quiet room. Maybe a person whose presence is comforting. Maybe just a feeling, a sense of safety, of belonging, of being exactly where you should be. Let that image or feeling settle in your mind. Don't hold it too tightly. Just let it be there, like a companion in the dark. The world is full of harsh light and loud noise, but it also contains softness and silence. Both are real, both are part of the picture. Right now you're in the soft part, the silent part, the restful part. This is where healing happens. This is where the body repairs itself, where the mind processes the day, where energy is restored. Sleep is not empty time. It's not wasted time. It's essential time, as important as any other part of life. Let yourself receive it. You don't have to do anything to earn sleep. You don't have to finish something first or prove something first. Sleep is not a reward for productivity. It's a basic need, like water or food. You deserve rest simply because you're alive, simply because you exist. That's enough. That's always enough. The words are thinning out now. There's less to say, less that needs to be said. The night is doing its work. The darkness is doing its work. The quietness is doing its work. You are a part of that work. Your resting body, your slowing mind, they are participating in something ancient and universal. Every creature that has ever lived has needed rest. Fish rest, birds rest, insects rest, even bacteria have cycles of activity and dormancy. Rest is woven into the fabric of life. It's not optional, it's not negotiable, it's built in from the simplest organism to the most complex. You are not outside this pattern, you are part of it. Your need for sleep is as natural as the need of a flower to turn toward the sun. Let that naturalness comfort you. You don't have to fight your body. You don't have to argue with your fatigue. You can just let it happen, like water flowing downhill, like leaves falling from a tree. Sleep is gravity for the mind. It pulls you down, gently, inevitably, into the dark. And the dark is not a bad place. The dark is where the stars become visible. The dark is where the fireflies glow. The dark is where dreams unfold, strange and vivid and free. The dark is rest. The dark is renewal. The dark is the other half of every day, as essential as the light. Let yourself fall into it. Let the darkness catch you. Let it hold you while you sleep. There's nothing to fear. The light will return. It always does. The sun has been rising for 4.5 billion years. It's not going to stop now. Tomorrow will come with all its brightness and noise and activity, but tomorrow is not your concern right now. Right now, there is only this darkness, this quiet, this rest. Sleep. Sleep now. Let go. The light will wait. And still, if you're here, let's continue. Let's let the words become even softer, even slower, even less urgent. Think about floating. Not in water necessarily, just floating, weightless, suspended. Imagine that you're lying on a cloud, or on the surface of a calm lake, or on nothing at all, just resting in empty space, held up by something invisible and gentle. There's no effort required to float. You don't have to swim or kick or paddle. You just let go, and the buoyancy does the rest. Sleep is like that. You don't have to make it happen. You just have to stop resisting it. The heaviness in your body, the slowness of your thoughts, these are signs that you're already floating. You're already on your way. Let your eyelids be heavy. Let your jaw be soft. Let your shoulders melt into whatever supports them. There's nothing else to think about. Nothing else to understand. Nothing else to do. Just float. Just rest. Just sleep. The room around you is quiet. The world outside is quiet. Even your own mind is growing quiet now. This is the threshold, the edge between waking and sleeping. You can cross it whenever you're ready. There's no rush. The other side will wait. And when you wake, the light will be there. Soft morning light, maybe, or bright afternoon light, or the gentle glow of a lamp. Whatever light greets you, it will have traveled a long way to reach you. From the sun, from the stars, from the bulb across the room. It will have bounced and scattered and filtered through the world before arriving at your eyes. And your eyes will open, and your rods and cones will fire, and your brain will assemble the signals into colors and shapes, and you will see. But that's later. For now, rest. For now, darkness. For now, sleep. The light will wait. It always does. Good night.